there are two questions that occur to me. The first, which is less important than the second, is just how plasma physics and nuclear physics are related. And second, of real crucial significance to our conversation, is how you feel about the movie Oppenheimer, which I mentioned earlier.
Well, I haven't seen it yet, so I can't tell you the answer to that. But I'd be happy to tackle a few of the issues to do with the application of nuclear physics. The main way in which, in my career, plasma physics and nuclear physics has been related is that in nuclear physics, there are two main processes of nuclear reactions. One of them is called the fission reaction, and that is if you take a heavy element like uranium and you break it up by some means, which we can talk about later, then when you do that, it releases energy. And that is the energy source of our current nuclear reactors and of the fission bomb, which was the first form of nuclear bomb, since you raised the question about Oppenheimer. So that's the fission reaction. And that's an important and incredibly powerful way of releasing energy. And nuclear energy in general, just to set the scene, is nuclear energy sources are approximately 1 million times more intense per unit mass than chemical forces. So when you make one fission reaction, you get out about 1 million times as much energy as you get from one, let's say, chemical reaction, let's say taking hydrogen and oxygen and making them into water. The second nuclear type of reaction is called a fusion reaction. And that is when you do the opposite. Instead of taking a heavy element like uranium, which has 200 and some number of nucleons in it, you take a light element like hydrogen, which has 1 proton, or its isotopes, which add a neutron or 2 to that proton, or other light elements like lithium and so forth. If you take, let's say, a couple of hydrogen isotopes and react them together, they can, instead of breaking up heavier elements, form a heavier element. In the case of hydrogen, they would form helium. And one can also address heavier reactions. But broadly speaking, a fission reaction is taking particles, gluing them together and getting heavy elements, unlike fission, which is taking heavy elements and breaking them up and getting lighter elements. But fusion reactions also release energy. At least they do when you're dealing with relatively small elements. And that energy source is the primary energy source of the sun and stars. In other words, the sun shines because of the fusion reactions that are taking place inside of it. So when a star is initially formed, it comes from neutral gas. The gas compresses, it heats up, it gets ionized, it becomes a plasma. But sooner or later, it gets so hot that it starts to have fusion reactions, and those are then the source of energy in the star. Now, fusion reactions are reactions between charged particles. So a hydrogen nucleus, which is a proton or a proton plus a neutron, or proton plus 2 neutrons, is positively charged. And if you react it with another hydrogen nucleus, they repel each other. And as a consequence of that electric repulsion of two similar charges, it's quite hard to make fusion reactions take place. You have to smash those nuclei together with rather high energies in the vicinity of hundreds of keV, or maybe tens under some circumstances of keV. Electron volts. We'll come back to. I'll explain this, but basically, energies, the sorts of energies that occur only at millions of degrees Kelvin temperatures. And so that's why in nature, fusion reactions take place in the incredibly hot centers of stars and other astrophysical bodies. But if we were able to create hot plasmas on Earth, hot enough so that those fusion reactions can take place, then fusion energy on Earth becomes, at least one hopes, as feasible as fission energy. And that's one of the driving forces that has encouraged scientists for 60 years or more to study plasma physics, understand it better, to understand whether, in fact, it's going to be practical to do that, to generate a well-confined plasma in which the energy doesn't simply leak away straight away, in which the temperature is hot enough for fusion reactions to take place. Now, in a star, the plasmas are held in by gravity. And that's the confinement force. Gravity is the confinement force that holds the star together and enables it to work. To do this on Earth, though, we don't have gravity as a feasible way of confining the plasma, because gravity is only strong enough at extremely large scales, larger than the Earth, sort of order of the size of a star, mass of a star anyway. And so we need, in order to try to make fusion work, we need a way of confining a plasma for long enough for it to react using immaterial forces, because you can't just put it in a milk bottle and expect that that's going to, be where your fusion reaction takes place, because either the plasma will immediately cool down or the milk bottle itself will dissolve and become ionized. And fusion research has basically been pursuing two main tracks to do that. One is to use magnetic fields, and that is so-called magnetic confinement fusion or magnetic fusion energy. And the other is to use what is called inertial confinement. And that is the idea that, well, if we just have a very small assembly of plasma that is incredibly dense and incredibly hot, that the reactions will all take place before it flies apart. So it's, in a certain sense, the inertia of the material of that body that will hold it together long enough for the reactions to take place. And these are magnetic fusion, and inertial fusion is sometimes called laser fusion, because typically lasers are used in order to form these incredibly hot cores of dense material that is going to react. Now, actually, we know that inertial fusion works, not because of lasers, but because the hydrogen bomb, so-called, is a fusion bomb. It is a bomb which is where most of the energy is coming from fusion reactions. But the hydrogen bomb is set off by setting off a fission bomb outside it. And so this comes back to this question of Oppenheimer and so forth, weapons and so forth. Nuclear weapons are ways in which the enormous available energy of nuclear reactions is released very quickly in an explosive way that has enormous power of destruction. The initial atomic weapons, so-called, were fission bombs, but within the next 6 or 7 years, people had learned how to spice them up and make them much more powerful by using fusion. So maybe I should stop there and you push us in a direction that you'd like to go.